Hello, Math 126 fans. We're going to talk about center of mass here. I'm going to peek at a couple homework questions, going to look at several old exam questions, but the main theme is these are not scary. I find that because we don't spend a lot of time on it in class, I sometimes get people coming to me and they're like, oh no, this is on old finals. I don't know what to do. And I want to show you that there's nothing to fear of center of mass questions on old finals. We could ask you about them. I know we didn't spend a lot of time here. Mostly it's just a chance for you to show us integration, but really the goal is for you to see something beyond volume. Okay, so let's look at these couple of homework questions. The homework questions are a little longer than an exam question would be. And then we'll look at some exam questions. So a lamina, which means a thin plate. So we have this thin plate, occupies the part of the disk in the first quadrant. So that gives us a region. 4. And what we've learned in chapter 15 is how to describe such a region. The question says to find its density, find its center of mass, if the density at any point is proportional to the distance from the x-axis. So that part is the one tricky part, maybe. I will say this in class, but the distance from the x-axis is y. That's what this is saying. So that funny thing there is saying that your density is proportional to, which means a constant, times y. And there's really only a couple things they could say. So the distance from the x-axis is 1, the distance from the y-axis, and then the distance from the origin. But we'll see that in the next question. Okay, so it gives me this. That's our function. We're basically done if we remember the formula. So the formula for center of mass is the following. We need to compute the double integral over this region, which we know how to give the bounds for that, of the density times x dx, and then divide by the total mass. I know that looks like a lot, but it's not a lot to set up. So the formulas, as we've seen, is that x bar is the integral of x times the density divided by the total mass, which is this. And then y bar, we do the exact same thing, except there's a y here. So that's all this question is. And then the other part of it is just a chance for us to show us your integration. So you'll do the same thing with y bar. It's going to look like k times y dA over the double integral of k y dA. And you have 3 integrals to compute. One of them is this total mass. So let's maybe look at that one first. But it's not like you have to rethink about the bounds. You already have them. So the bounds I would use is polar. That's my choice here. You could choose something else. And it's going to be 0 to 4. And then if I'm doing the total mass, it's k times whatever y is, which in polar is r sine of theta, whatever dA is, which is r d theta. Then you're computing. So it's going to be the integral from 0 to pi over 2. So mostly this section is a chance to practice more with computing your double integrals. This is going to be r to the third sine of theta from r equals 0 to 4 d theta. So it's going to be 4 to the third over 3 times k, the integral from 0 to pi over 2 sine of theta d theta. And then we'll compute that. So that's going to be negative cosine. I think you end up getting 4 to the third over 3k. That's what you're going to put in these spots. Then you're going to compute the other things. So what if there's an x in there? That's going to change this. So you're going to compute these 3 numbers. I computed one of them for you. And then you're going to divide, and that's going to be your center of mass. So yes, It's some computation, but it's not scary to set up. Okay, so your other homework question says something similar, except that it says the density is inversely proportional to the distance from the origin. The distance from the origin is x squared plus y squared. Inversely proportional is this. I think on a final, I'd remind you of what that is and give you a few more details. But they're telling you that. You're then going to start computing based off of whatever region they gave you. So what do you have to know to get ready for the final exam on this topic? You really just need to know these formulas, which everyone's going to have on their note sheet anyways. So let's look at some old exam questions. So here's one right here. I'll move these out of the way so we're not distracted. So it says a lamina occupies, so this is question 6 on the fall 2021 exam. A lamina occupies the rectangle. Find its center of mass as the density at each point is given by this function. So they're giving me this rectangle that's 0 to 4 and 1 to 2. And you can set it up any way you want, but there are 3 integrals you need to compute. The double integral over that region of x times the density, the double integral over that region of y times the density. Those are called the moments. And then finally, you need the total mass. After you've computed those things, you'll put them together and get x bar is, let's call this something, 1, 3, 2. X bar is going to be 1 over 3. Y bar is going to be 2 over 3. And then you would stop. They've told you the function, so they've told you what goes here. They've told you the region, so you actually know the bounds. The bounds would be, 0 to 4 and 0 to 2 of x plus y squared dy dx. And, I did not multiply by the x. X times x plus y squared dy dx. Distribute, integrate with respect to y. So it becomes we really are using this to check on that double integral setup and integration. Here's another one from an old test. Proportional to the distance from the y-axis, so that's this way, so that's the density of k times x. So I will post on my lecture notes, the 3 different translation things, which I've already discussed in this video here. But then you draw the region, you set up the integrals. Oftentimes these questions will just ask for x bar or y bar, but you do have to compute a little bit. So this is usually a problem we're using to compute. It shouldn't be a scary problem in terms of setup. They give you a region, you put the bounds, you start computing, and you have 3 integrals to compute. Yes, it's 3 integrals, but it's a chance for you to show us your double integral skills. All right, I hope that explains the idea.